Hey, what's up YouTube? Today I'm going to demo a small handy blueprint tool I just released on my Patreon as a tier 3 reward. I will also do a quick breakdown and show you how the blueprint was built. I won't get into too much detail though, I kinda want to keep this video short for once, but I'll hopefully explain enough to get you started if you're interested in building such tool. Alright, let's dive in. So, if you're familiar with runtime virtual texture in Unreal Engine, well, the tool I built is more or less a very naive and old school alternative. Now, don't get me wrong, RVTs are great and this tool is by no means meant to be a replacement, okay? However, you might have your reasons not to use RVTs, or even if you do, you might still be interested in capturing a top-down view of your scene and assets the good old way and have access to a simple static texture, right? And this tool does precisely that, with quite a few extra very interesting features. It's not perfect, but I'll go over the few limitations this tool has in a second. Alright, let's go through different use cases step by step. So here I have some kind of test scene. I have a landscape with a dirt, grass and rock layers. Nothing too fancy, don't worry about how it looks, it's just a quick demo. Now let's say I want to mimic what using RVTs would allow me to do, meaning amongst other things, blend an asset with this terrain based on color, roughness, specular, normals and world Z position. And if you're not familiar with this idea, I'll let you take a peek at my latest stylized grass video, where I quite extensively go over how RVTs can be used to do just that. Anyway, so I'm going to drag that blueprint tool in that scene, add an actor and pick the landscape. I'm then going to create a render target, set its resolution to say 512 and its format to 8 bits RGBA and assign it here, then press capture. Okay, that seems to have worked. I have some kind of debug info about the capture size and X and Y location, and the captured volume is highlighted for a certain duration. Durations that I can tweak here if desired, but I can also click here to show that debug info at any time and clear it as well if needed. Debug views are also available, so let's first check the projected debug view. If I then increase the plane size and move that blueprint around, I can see that the captured texture is indeed projected at the right location and size. The second debug view allows me to check individual channels, red, green, blue and alpha channel. And right now the texture has no alpha channel because the RGB scene color was captured, so let's render something in that alpha channel. At this point I'm content with the red, green and blue channels, right, so I can untick them here and only write into the alpha channel from now on. However, I'm still only rendering the RGB base color, so here I can swizzle channels and decide to render, say, the red channel into the alpha channel. Capture and voila. Now, having a duplicated color channel isn't useful at all, so let's render something else, like say the roughness. And there are a few solutions to this. You could, for instance, temporarily tweak the landscape material and render the roughness as base color, but there's a much simpler solution, which is to change the post-process material here. Right now it uses this base color post-process material, see, it just grabs the diffuse color buffer. So I've built a few post-process materials that might be useful, like this roughness one. It's nothing complicated, see, it just outputs the roughness buffer really. Press capture and voila, roughness is composited into the alpha channel. Sweet! There are two things to really keep in mind though. First, this does not output any alpha value, right? So to actually composite that grayscale roughness value in the alpha channel, any of the red, green or blue channel must be quote-unquote rewired to the alpha channel, like I have done here. Second, if I want to capture negative values, like say normals in world space or values that may go beyond a 0 to 1 range, like again normals in world space or the Z world height, I must use at least a 16 bits render target, right? So let's actually test this, change this to 16 bits, and I'm going to start from scratch, so press clear. By the way, the clear color can be changed here if needed. Now I'm going to, say, render the normals in world space in the red and green channel. The Z component can be reconstructed in shader, and I'll show that in a second, so I can skip the blue channel. And in that blue channel I'm instead going to render the world Z height, and then say the specular in the alpha channel. I highly recommend to only render 0 to 1 values in the alpha channel, else it can screw up everything. Working with the alpha channel in render targets is a gigantic pain in the butt for some reason, I absolutely hate it. Anyway, let's create a second render target, this time 8 bits, update it here. Then render the base color in red, green and blue, cool, and the roughness in the remaining alpha channel. So you see, you can use an iterative process and composite things one step at a time, and I've only scratched the surface. Anyway, once I'm happy with the result, I can convert those render targets to static textures. Now let's create a test material, and then I'm gonna bring those two textures in and use a small material function bundled with the system to build the correct UV coordinates. It just needs the capture X and Y and size coordinates the tool outputs upon capture, like so. Then let's see, if I recall correctly, this texture has the base color in RGB and roughness in the alpha channel. And that one has the X and Y world normal in red and green, so first I need to recreate the world normal Z component using this derived Z function. It's still in world space though, so transform it to tangent space, or I could make this material use world normals, works either way. For the Z position stored in the blue channel, well, just for demonstration purposes, I'm going to subtract it to the current vertices Z world position, build an up vector with that scalar value, and plug that in the world position offset, and the specular in the alpha channel. Cool. Now let's add, say, a sphere, apply that material, and voila! What you're looking at is this sphere mesh projected in Z onto the captured world height. It has normals, roughness, specular, and base color that all perfectly match the underlying surface, and so it blends with it quite nicely. And so I've recreated sort of what you can do with RVTs, right? But very, very naively. And let's step aside just for a minute. I say naively because one of the key features of RVTs is the ability to stream in and out of memory just what's needed of a texture. Meaning, say you want to render your landscape base color, normals and whatever else, but that landscape is super large. Well, then to have a somewhat decent resolution, you then need a super high-res texture, which may fit in your memory budget, but may also probably not. And what runtime virtual textures do, essentially, is to split that giant texture into small tiles and render only the necessary tiles depending on the view and at the required resolution depending on the view distance, and it's all cached. So it's much smarter than having a giant texture loaded at all times in memory, right? RVT only render what's needed when needed. But I'd say it's also a bit of its weakness. A virtual texture system is not trivial to implement by any means, and despite epic engineers having done a darn great job, RVTs may still suffer from a few instability and flickering issues here and there, depending on the available VRAM, available RVT memory pool, and a bunch of other obscure settings. And so, as usual, it's all about pros and cons. Nothing is perfect, and you might prefer this naive approach as long as it makes sense, right? I don't see this usable for large open world, you know what I mean. Plus, you might still have a use for this kind of tool despite using RVTs, so again it's not really meant to be a replacement. Moving on, there are still a few extra features I've yet to show. So, I've essentially captured this landscape color, roughness, specular, normal, and world height. What if I want to render some kind of landscape mask? Well, here I created a very simple landscape material that just samples the dirt layer for the base color, right? I'm going to create a third render target, red channel 8 bits, and set it here. Select my landscape, override its material with the one I just showed, capture, and voila, there's the dirt mask. I can then sample it here and say, I don't know, drive some emissive color when that mesh is over some dirt. And that texture could actually even be much lower resolution, right? Don't forget to convert it to a static texture once you're done though. Anyway, I can also choose to blur the capture, or apply some kind of processing before or after the blur pass. Say I want to apply a contrast to that dirt mask. Well, that's super easy. Create a material, set it to masked, set the mask clip value to 0, this is important, allow negative emissive values, and down there this use with editor compositing option must also be ticked. Then create a texture sampler parameter, set its name to texture, important, and then do whatever you want with it, like add a cheap contrast to both RGB and alpha channel. Then add a parameter named, say, contrast, then in this texture post-process materials, add this newly created material, add a scalar parameter override, and specify the name. Now to compare, let's first do a capture without any blur nor contrast, okay? Then add some contrast, capture, and voila, that's cool. And you can shade multiple processing effects with that array, right? Like say, then run some kind of edge detection algorithm. This one has 2 parameters, so add them here, tweak them, press capture, boom. And then why not add one more to convert the result to a tiling texture? Voila, isn't that awesome? But it gets even better. I can use an additive or subtractive process to further iterate on the texture. Say I'm happy with that tiling dirt mask texture. Not sure what I'd use it for, but anyway. So let's tweak this landscape override material and this time sample the rock layer. Then change the mode from override to additive, and tada, the rock layer was added. Now this additive and subtractive process might be a bit finicky to work with, especially with the alpha channel for some reason, and how much you can iterate on the texture using this process also greatly depends on the render target format. 8 bits has a very limited range, so you can only do so much with it, right? But still, it might allow you to do cool things. There's also one extra feature I want to show, and one that could have been great. Unfortunately, I couldn't get it to work with landscape for some reasons, so it's quite limited, sadly. You see, I had to manually override this landscape material to capture this mask. It's no big deal, but let's say I have a dozen of extra actors like here and I want them to write a specific value in that capture mask. It'd be annoying to select every single actor and change their materials, right? And so there's this global material override that allows me to, well, override those actors' materials just for the time of the capture and possibly customize that material with extra scalar and texture parameters as well. Sadly, however, updating a landscape material in Blueprint seems to be broken. I couldn't get it to work, so it's limited to actors for now, but then manually updating just the landscape isn't the end of the world, I guess. Oh, and also I may even override material per actor if desired. So let's do a quick demo. Say I want to render a black and white occlusion mask to mask out some rain effect inside buildings. I'm going to render the landscape with a simple white material, then pretend those cubes are my buildings, add a global override with a simple black material, press capture and done. Then say I want one actor to be green in the capture for any reason, add an override on, say, that actor with a green material, capture, and voila, sweet! One very last small feature I want to showcase. So right now the capture area is computed from the listed actor's overall bounds, right? You can, however, change this with these settings and switch to manual mode. You can then move that actor around and scale it, rotation has no effect, to precisely select where the capture takes place. Make sure that actor is above surfaces you want to capture though. And voila, that's pretty much it. I think it's kinda cool, and weirdly enough, the blueprint is actually quite straightforward to build. Alright, this tool mostly relies on a simple scene capture component, and really there's only a couple of important settings to know and one key principle to keep in mind to build such tool. Let's have a look at it step by step. Most of the logic happens in that capture function, set to be callable in editor. First, I check if the user has specified any render target and check that its resolution is valid as well. Then check if the user has specified any actor to capture and double check that the scene capture component is valid as well. Then I create a buffer render target, because I actually don't want to capture directly into the specified render target. That wouldn't allow me to control how it's composited. And again, here the main feature of this tool is to enable some sort of iterative workflow, right? So I wouldn't want this capture to erase what's first in that render target. And so I make this capture component render into a capture buffer that has the same size and format than the render target specified by the user. Then here I apply the global material override, meaning I create a dynamic material instance, pass it to this function to set its scalar and texture parameters, then loop through this list of actors. Then for each actor I get all their primitive components, and for each component I loop through all their materials, which are replaced with this override I created. I also keep track of materials replaced that way, so I can restore them after the capture. That's the tricky part, but fortunately using a simple map to bind components to their original material helps a lot to ease this process. Same thing happens here, but per actor, right? Create dynamic instances, apply parameters, override primitives materials, nothing too complicated really. Once that's done, I set up the capture component. So first I ensure its base settings are all correct. Source must be set to final color if I want post-process materials to be applied to the render. Capture must be set to orthographic. It must also use its only list to only include the desired actors. Then use the override mode. I could use the additive mode, but then I'm going to do that myself, because I want to support a subtractive mode as well, and possibly swizzle channels, so I want to have control over that process. Then make sure its show only actors list is empty for now, and these two settings must be set to false and this one to true to render post-process materials. That one was frustrating to troubleshoot, it drove me nuts. Anyways, then here I just access this scene capture post-process structure to ensure that it has no post-process materials to begin with. Then I figure out the capture's location, rotation and orthographic size, either based on this blueprint's location and scale if mode is in manual, or based on the list of actors if automatic. And that's super easy, there's this simple handy blueprint function that does all the dirty job for you. Once I have that figured out, it's actually set here. I also pass along the capture buffer I want to render to and set it here. Remember, I don't want to capture in the render target specified by the user, I want to capture in a buffer. And here I set the list of actors to render. Then I create a dynamic instance of the post-process material to apply, if any, set its parameters, and update the scene capture component structure accordingly. At that point, everything is ready to go for the capture, so do that. Then using the maps I stored here, I loop through primitives that had their material changed and give them their original material back. And finally, I apply any processing and blur effects to the capture buffer and composite that buffer into the user-specified render target. Now, there's a key principle to understand here. I have that capture buffer I need to composite into this render target. Alright, let's try and do this. Create a material, create a texture parameter for the capture buffer and one for the render target. Then choose whatever method I wish to use to composite the two, say a simple add, right? Then create a dynamic instance of that material in Blueprint, so I can set those two texture parameters, one is the capture buffer and one is the render target. Then call the draw material function, and I want to draw in that render target, right? Well, unfortunately that's not possible for the simple reason that if I were to do that, I'd be both reading from and writing into this render target at the same time, and that can be done. So the way around this is to first copy this render target into a buffer and have that material sample that buffer instead. Same result, but this material, when drawn into this render target, no longer has some sort of read and write conflict going on, okay? And to achieve that, all you have to do really is to first create a very simple material that just samples the texture parameter. Then in Blueprint, create a dynamic instance of that material, set its texture parameter to whatever texture you want to copy, create a buffer render target, and draw that copy material into it. Voila, that buffer, as long as it has the same size and format, should be identical to this render target. And then update that quote-unquote composite material to no longer sample that render target, but the copy, right? Hopefully that made sense. And that's exactly what happens in all these functions. In every single one of them, I first create a temporary buffer, then create the material to copy the capture buffer passed along, and draw it to copy it. Then here I create a dynamic instance for the specified effect material, have it sample the temporary buffer, and write the result into the capture buffer. So you see, it's always a game of avoiding that read and write conflict. Whatever render target you're trying to write into cannot be read from, and so if you want to do that, you have to copy it in a buffer first. For the blur effect, same principle, but it's even simpler. I don't even use a blur shader. All I do is create a temporary buffer that is half the size of the capture buffer, and I continuously copy it to the half-res buffer and back to the full-res buffer, so that it's continuously downscaled and upscaled, and that blurs the texture. Super easy. Anyway, once the blur and effects are all applied to the capture buffer, it still needs to be composited into that render target, right? Because remember, the capture happened in the buffer, and effects, if any, were applied to it as well. That render target wasn't modified at all yet. And that's the role of this composite function, and I'd remain somewhat vague, because really there's no need to go overboard. You could choose to have a simple add or subtract material, like I showed a minute ago. Here I overcomplicated things to allow channels to be swizzled and to choose which channels can be written into, so I pass all kind of data to a material that is designed to do all that. It's nothing too complicated, but I'm a bit short on time, so I fear I'll have to let you take a peek at the project files if you want to take a closer look. It's available as a tier 3 reward on my Patreon. Voila, this video was a bit more of a demo than a breakdown really, but hopefully you still learned a couple of things along the way. The next 2 videos are going to be about cool Niagara techniques, so stay tuned, feel free to leave a like and subscribe to the channel if you like the content. Thanks for watching, thanks for your support, I'll see you in the next video, please take care of yourself. Bye bye!